Hello and welcome to your first video on wood. In this introduction, we are going to learn about the anatomy and some of the strength basics of this beautiful organic material. With wood, you have choices of using a lot of small repetitive members like we see in the roller coaster or in the custom home that's being built in the bottom right corner. But you can also create engineered lumber, gluing pieces together, modifying to give you additional strength. So you can have long open spans like we see in the church, much like you would have with steel, or this arched bridge. And we're going to learn more about engineered lumber and a new wood construction material called cross-laminated timber as the course continues. To get into understanding wood for construction, we have to make sure we understand that there are two main types of wood that comes from our two main types of trees. And of course, that's hardwood and softwood coming from our deciduous or evergreen trees. So in the United States, we do not use hardwood as a construction material, but we do use it as a finish material. So whether it's for furniture, flooring, wood cabinets, trim, doors, etc. While it's called hardwood, it is typically harder than softwood, but not always. You should note that balsa is a hardwood. In the United States, we use softwoods as construction lumber, primarily Doug fir larch, hemp fir, and southern pine. But around the world, you can have hardwood as a construction material if that's the wood that more commonly grows in your area, specifically in the tropics where it grows very quickly and you're not likely to see a lot of evergreens. When we do cut lumber, rectangular lumber, out of a circular log, there are multiple ways to do cutting. The most common are quarter sawn, rift sawn, or plane sawn methodology. We're going to learn a lot more about this later, but it is important to note that quarter sawn and rift sawn give you a better quality, more dimensionally stable lumber, and so that's what's typically used for hardwood. You get more lumber out of the log if you plane sawn it, but it's not as high quality a piece of lumber, and that's what's used for construction grade. We need to look at the anatomy of the tree itself, though, to understand how we get strength from wood. So let's just start where all the growing begins, and it's actually this tiny little fuel cell thick layer called the cambium. And the cambium exists between the wood and the bark. And it's not that dark ring you see around what we typically would call bark. That dark ring is your inner bark. It is such a microscopic layer we can't see it, but that's where all the growth occurs. So as we move inward, we're going to have the youngest wood closest to the cambium layer, and that wood is called our sapwood. It is young, it's your outermost ring, it's still living, so it's going to be where your tree is transporting water and nutrients up and down the tree. Now, today, we like to talk about using managed forests because they're greener. We can make sure that it's managed in such a way that we're not clear cutting, we're not cutting old growth, but then you're having second, third, fourth generation trees, and they tend to be cut at a very young age and a small diameter, maybe 9, 10 inches. So you have primarily sapwood in what you're cutting. The reason that that could be an issue is that inner, darker layer is called your heartwood. This is the oldest part of your tree, and it's the strongest and densest. It's no longer living and is annually getting compressed smaller and smaller as the tree continues to grow. So that strength is lost when you're cutting down a small tree, and these managed forests that harvest young trees end up having very limited heartwood in the lumber. The heartwood is also regularly gaining resins as it ages, and those resins help resist decay and insect attacks. You may have heard of things like cedar wood or redwood being great as an outdoor wood because it protects from insects and rot, but that's only true of the heartwood. If your lumber has sapwood, you do not have any of this protection. Finally, the innermost point of the tree is the pith, and this is your year one growth. Not really important, it's just interesting. Now, the final thing we're used to seeing when we look at the cross-sectional log are the growth rings. And so the annual rings really include two rings, and we can see here a darker and a lighter ring. In our case, this is for the rainy and the dry seasons, and the lighter colored larger ring, that's your early or spring wood. It's made of very large open cells, a very fast growing ring, versus the darker, smaller ring, that's your later summer wood that comes when the tree is relatively dormant in its growth period. And so you end up with these much denser, tighter cells. If you looked at a schematic of the cells, we'd actually see the very tight, light, late wood versus the open, more porous early wood that just doesn't give us the same density and strength. It is important to note that if you're talking about a tree that's from the tropics, where you don't have real prominent growing seasons like you do somewhere like North America, then you're not going to have as prominent of rings, and sometimes it's much harder to age the trees. Now, these cells that we see in our late wood and early wood, we can also look at them through a scanning electron microscope, and so we can see up on the upper left of this image the late wood and then the much more open-celled early wood near the bottom right. And as we turn and we look down vertically, what would be down longitudinally or the trunk of the tree, we can actually see that those late wood and early wood cells are long, skinny tubes, and those tubes would run the height of the tree, being broken up occasionally. Now, those tubes are called tracheids. In a softwood tree, they make up about 90% of the volume of the tree. They're very important because not only do they transport nutrients throughout the tree, they provide all the mechanical support for your tree. If we're talking about a hardwood, now we have a second scanning electron microscope image. Not only do you have the tracheids pointed out with the T, but you also have the vessels, which are the capital V. They also help transport nutrients. And then between the tracheids, you have thicker fibers that provide additional mechanical support. Both the softwoods and the hardwoods have horizontal cells, being about 10% of their volume, and those are called rays, and they just help transport the nutrients and the moisture horizontally through the tree instead of vertically. Now, the tracheids are critical to understanding strength because they lead to the anisotropic behavior of wood. By anisotropic, it has different strengths in different directions. Steel is isotropic, same strength, tension or compression, and no matter which direction you're coming at with your tension or compression load. Wood is strong parallel to grain, but relatively weak perpendicular to grain. And what is that? What does that even mean, parallel to grain versus perpendicular to grain? Well, let's take a look at a piece of lumber. So if we look at the end cut, the side there, we can actually see sections of the rings where we've cut this board out of the log. And as then we go down the trunk of the tree or down the length of the board, we can see the grains. And in this case, the grains as we see them, our side of our cut there is perpendicular to the rings. So what happens if we have a square cut? Here's a 4x4. And so again, we can see the rings on the face. We can even see a knot where a branch was growing out of the tree right up through that face there. And then up on the top, we can see the grains as they relate to the rings, but those grains look different than our first example. And in fact, if we look on the left side of our 4x4, we see nice straight grains that sort of match our 2x4 example on the left side. And the reason that we're seeing different grain patterns on the top and the left side of the 4x4 is our orientation to the rings. So on the top, our rings are almost parallel to the side of the 4x4, and so we're seeing what's called face grain. On the right, our rings are perpendicular to the edge of the board, just like they are on our 2x4, and so we see what are called end grains. But oh, this is really cool. Check it out. On both of them, we can actually see heartwood and sapwood. So this was cut nearer to the center of the tree, so we have some heartwood, and there's a little bit of sapwood on the edges. So this would be actually a higher quality board because of the heartwood content. So we see the grains. We see that we said the strength is different if we're parallel or perpendicular to the grain, but how do tracheids provide our strength? Well, to understand this, we actually need to think about straws. So here we just have a bundle of straws, and we're going to imagine that the tracheids are just a series of straws up and down the vertical length of the tree. And so if we were to load straws in compression, and we've done this before, if you take a straw and you load it in compression, and so parallel to the grain or along the long axis of the straw, it fails by buckling. And so tracheids in compression get their strength by their resistance to buckling, and that's the failure mode, is buckling of the tracheid cells. In tension, I want you to imagine pulling on those straws. Now, you have two possible ways to fail. One would be to pull the straws out of the other person's hand, which we're going to assume we don't have a hand holding on to our tree. So if we want to really see how the cells themselves, we would have to rip the straws apart. And that's actually the failure mechanism of wood in tension. We rip apart the covalent bonds in the atoms that make up the tracheid cells. And so because of that very strong bond, theoretically, wood is much stronger in tension than it is in compression. But wood is an organic material. And in fact, in our sample that we looked at, there was actually a knot. And if we look closer at that knot, we can actually see that our grains are discontinuous around the knot. Some of them completely stop, and you could pop that knot out. Some of you may have looked through peepholes in fences where there had been knots in the fence board and they've just been popped out. They are a discontinuous, brittle material. Now, if you remember from strength and materials, if you have a member loaded in tension axially and there's a hole, the stress has to move around the hole. It can't pass through it, and you get a stress concentration. So it raises the stress that your member experiences, bringing you closer to the failure loads, even though you might not have a very high load. Versus in compression, we filled in our hole there with our knot of wood. If I push on that in compression, each side of that just presses against the knot, and the knot is able to transfer the load through. So it makes absolutely no impact in compression. It turns out that because we don't always know how large our knots are going to be and what they'll do to us stress concentration wise, the codes have set it up that the allowable stresses due to tension are lower than the allowable stresses due to compression. Even though if you had a perfectly clear board without any knots or imperfections, you should have much higher strength in tension than compression. But that's parallel to grain. What about perpendicular to grain? We said the strengths don't match. So how do the tracheids provide strength perpendicular to grain? Well, if you just think about going sideways on one of those straws, basically it's like pinching the straw. We're just compressing the cell walls, and it fails by crushing of the tracheid side walls. And in fact, here our bottom horizontal member is being loaded perpendicular to grain, while the vertical member teeing in is parallel to grain. And you can see on our horizontal member that we are crushing, and we're literally just crushing the side walls. If we think about perpendicular to grain in tension, be like pulling up on those tracheids. If you have a bundle of straws and you try to pull them apart, there's nothing holding them together, and they're just going to fall apart like our straws here do. In fact, it's such a bad idea to load wood in tension that we just don't do it. And you won't even find an allowable stress for loading wood in tension perpendicular to grain in any of the building codes. So these are the basic ideas of strength in the wood, but what are some other factors that could affect the material properties? Well, one is moisture content. How much moisture are in the actual tracheids and vessels versus the cell walls or the open space in between? Defects. How many of these knots do you have? How is the board warped, or what state is it in? We have the duration of the load and the orientation of the grains with respect to the loading. So how long is that load going to be on there? And is the stress I'm creating parallel to grain, perpendicular to grain, or has my board been cut such that I'm at an angle to grain? So all of those are topics we'll be talking about in the next video. Thanks for watching.